So on homework 4, number 5 asks that if m is greater than 3, prove that 5m is even. So again, this all comes down to prime factorization. So let's rewrite this term as phi of p1 to the a1, p2 to the a2, all the way pn to the an. So again, with multiplicative, since the function's multiplicative, we can separate this out. So p1 to some exponent, phi of p2 to some exponent, all the way to phi of pn to the exponent. Now, then we can reduce this a little more. So then we can rewrite this expression as p1 to the a1 minus 1 times p1 minus 1. And that's equivalent to 5p1a1. So if you have questions on how we got this expression, remember that phi of n equals n times the number times the product of all the divisors, prime divisors dividing to n with 1 minus 1 over p. So if we plug in this expression, we get that p1a1 times 1 minus 1 over p, because the only prime that divides into p1 to the a1 is just p1. So doing some math, we get p1a1 minus p1a1 minus 1, and then we factorize it, so it's p1a1 minus 1, and then we just have p minus 1 on the outside. So then what can we do from this? Well, if p is odd, then p minus 1 has to be even. So no matter how many odd numbers we multiply together, if we have one even number, the whole product's even. So that we're pretty much counting for every single situation. But we have one more case. What if p is even? That only happens if p equals 2. So then p minus 1 is just 1. But recall that now we have 2 to the a1 minus 1. And since m has to be greater than 3, that means a1 has to be a1 has to be greater than or equal to 3, because 3 minus 1 is 2, so this will be 4. So since it's 2 being raised to any exponent, that's still just going to give me an even number. Multiplying anything else, it doesn't matter whether they be odds or evens. Since I have one even number, the whole term's going to be even. Therefore, 5m will always be even, given that m is greater than 3. I explained 6 in a separate video, so we'll go straight to 7. So this relates to the Chinese remainder theorem. So they're basically asking me to solve for x is congruent to 3 mod 7, and x is also congruent to 5 mod 9. So remember that for 3 mod 7, think of base cases that work. So like 10, 17, 24. What's going on? I'm increasing by 7, right? So you can think of it as that slope. So I can represent this as 7t plus 3. So if that's a solution for x, that also must satisfy this. So really, I can say that 7t plus 3 is congruent to 5 mod 9. So all I did was derive a solution for this and plug it into the second modular equation. So now from this, let's do some algebra. So I can say 7t is congruent to 2 mod 9. And then a little more, so then this is negative 2t is congruent to 2 mod 9. So this is t is congruent to negative 1 mod 9. And let's just get rid of this negative, so it's t is congruent to 8 mod 9. So notice that it's mod 7 and mod 9. So to figure out what my final mod would be, we can just represent some number n, such it's just 7 times 9. And then I just got these from what modular numbers I'm taking to. So this will give me 63. So my final answer is going to be something mod 63. So recall that t is congruent to 8 mod 9. But remember, x is 7t plus 3. So that's where the mod 63 comes in. I can put this here, mod 63. Because recall that if 63 divides into a number, that means 7 divides into it as well. So this still satisfies the original equation. But now the 63, what that accounts for is like, then now 9 will also divide into that number. So now with x equals 7t plus 3 mod 63, I plug in my expression for t. So then I have 7 times 8 plus 3 mod 63, then which gives me 59 mod 63. So then the last problem is a little more extensive. So it's saying x is congruent to 5 mod 7, x is congruent to 2 mod 12, and x is congruent to 8 mod 13. So the idea here is still going to be the same. I like to think of it as like you're solving one equation, plugging into the next, and then plugging into the next, and finally you piece all the information together. So you can think of it as like a system of equations, but you're taking it one at a time. So think of your base cases for this one. 12 plus another 7, 19. Yes, 19, then 26, 33, etc. So I can represent this as x equals 7t plus 5. So that represents a solution. So then what do we do from here? Well, set it equal to the next modular equation. So let's say 7t plus 2 is congruent to 2 mod 12. Sorry, this is 5. So then let's do some algebra. 7t is congruent to negative 3 mod 12. That's 7t is congruent to 9 mod 12. Multiply each side by 5, so I have 35t is congruent to 45 mod 12. This gives me negative t is congruent to 45 mod 12. This is going to give me t is congruent to 3 mod 12. So finally, I can represent this expression as, well, I found t, but remember I have one more equation. So that's where I can denote a new variable. So let's say t prime is congruent to is equal to 12t plus 3. And this is just derived from my previous expression. So think of cases like 15, 27, add another 12, 39. All I'm doing is incrementing pieces of 12 so that when I subtract 3, it's divisible by 12. So now with this, I'm going to plug it into my third and final equation. So recall that we had originally 7t plus 5. But now this t is going to be a prime because we know the solution here. So if I have a t prime here, just replace whatever t prime here, whatever this t prime is, with 12t plus 3. So that gives me 7 times 12t plus 3 plus 5. So this gives me 84t plus 26. Now this is where the final equation comes in. This solution, remember originally, is a solution to x. So x also has to satisfy this congruence. So with this plugged in, I can say that 84t plus 26 is congruent to 8 mod 13. Okay, so let's do some algebra. So we have 84t is congruent to negative 18 mod 13. So then it's 84t congruent to 8 mod 13. Then I can say that's 21t is congruent to 2 mod 13. A little more, so that's 8t is congruent to 2 mod 13. That gives me negative 5t is congruent to 15 mod 13. Then I can divide each side by negative 5, so t is congruent to negative 3 mod 13. So let's just make that positive. So that's t is congruent to 10 mod 13. Final thing, so now we went through all three equations. So remember, for the final solution, we just multiply these together to figure out our final mod. So 7 times 12 times 13, this is going to give us mod 1092. So intuitively, that means that if 1092 divides into a number, so does 7, 12, and 13, which is what we want, so that x satisfy all three equations. So now we know what modular it is. Our final step is that since we have t equals 10 mod, t is congruent to 10 mod 13, let's plug that into what we had. So we have 84t plus 26. Well, I know what t is now. 84 times 10 plus 26 mod 13, or mod 1092 now. So a little more, I have 840 plus 26 mod 1092. And that's going to give me a final of 866 mod 1092. So that is my final equation.